Hello and thank you for joining me for another video. My goal is to keep you informed and entertained today with this content. This video is all about the Poisson distribution. Imagine we are inside the branch of a commercial bank and the teller estimates that on average 5 clients per 5 minutes arrive at the bank. The branch manager, however, has scheduled a cash replenishment for the first 5 minutes of the next workday and for security reasons wants to estimate the probability that no clients have arrived at the bank. So we need a model that can describe discrete events occurring in a fixed period of time. This time interval is 5 minutes in our example, with a known long-term average rate. This average is denoted by lambda and is equal to 5 clients in our example. Independently of the time since the last event, we suppose that the arrival of any client is not dependent on the arrival of any other client and ranging from 0 to infinity. To devise such a model, we do not need any special skills. The only thing we need is a time machine. We will use it to travel through time to Paris back in 1837. There we have a lot of things to do. We have to visit the Louvre Museum, the Notre Dame, take a stroll along the Seine River. The last thing we have to do, however, is to meet with a prominent figure in the mathematical community of Paris in the early 19th century, and this is Siméon Denis Poisson. He was a member of the French Academy of Sciences and made important contributions to a wide range of mathematical fields, including probability theory, statistics, analysis, and mechanics. He just publicized a paper with a probability distribution that could be used to model the number of times a certain event would occur in a given time period, assuming that the time at which the event occurred was constant. In his paper, we can find a formula that can be used to solve our problem. The probability that X number of events will occur within the defined time interval is equal to the average rate of events, represented by lambda, raised to the power of x. We then multiply this by m, raised to the power of negative lambda, where a is the base of the natural logarithm and is approximately equal to 2.72. And finally, we divide the product we obtain by the factorial of x. And we have made a short video about what factorials are and how large of numbers they can generate. If we use this mathematical formula in our example, and given that the factorial of 0 is equal to 1, we find that the probability that no clients will come to the bank during the first 5 minutes of the next workday is close to 0. Therefore, the branch manager has decided to take increased security measures during the cash replenishment process tomorrow. However, this formula may be difficult to remember, and the calculations it involves may sometimes be challenging. For this reason, the easier solution to problems like that can be offered by Microsoft Excel. So here we are, we have opened Excel. So in order to calculate the probability that no clients come to the bank for the time interval of 5 minutes, we will use the Poisson distribution function of Excel. So we start typing Poisson.dist, that's the function. We open bracket. The first argument is the number of x, that is equal to 0, because we want to calculate the probability that no clients come to the bank. The second argument is the mean, that's the lambda, that is equal to 5, as we have previously discussed. And the third argument is to determine whether we want to calculate the cumulative or the non-cumulative probability. In this case, we want to calculate the non-cumulative probability, so we will insert the value of 0. So the probability that no clients come to the bank is closed, is almost equal to 1 to 0%, let's say. If we want to estimate the probability for x being equal to 1, 2, 3, 4 until 15, we can copy the formula. And so here are the outputs of the same function. Now, if we want to calculate the probability that less or equal than 3 clients come to the bank for the same time interval, we will use the same probability function of Excel, but we will insert the value of 1 as a third argument because we want to estimate the cumulative probability. So we start typing the equal sign, Poisson.dist. The first argument is the value of 3, the second argument is the value of lambda that is equal to 5, and the third argument is equal to 1 because we want to calculate the cumulative probability. So it is close to 26%, and it is exactly equal to the individual probability for x being equal to 0, 1, 2, and 3. Let's check this, and we have exactly the same result. We can copy the formula for the other values as well. So the output of the cumulative probability increases until it reaches 100% when the value of x is equal to 15, when 15 clients are supposed to enter the branch for the 5 minutes time interval. Now, if we want to present these outputs in a graph, in a Poisson graph, we can select these values, and from the menu bar we check Insert, Recommended Charts, All Charts, Combo, a combo chart, and because, as we can see, the highest individual probability is close to 18% and the highest cumulative probability is close to 100%, it could be better to include a secondary axis for the cumulative probabilities. So here we are. We can delete the grid lines. We can delete the legend as well. We can select darker blue for the individual probabilities, so as to have a better contrast. Here we have a darker blue. And we can insert a title like this, like the title of the table. I can make it bold if I want. I want to add access titles. So here I have the number of clients. Here we have the cumulative probability. And here we have the individual probability. I think we have a nice graph, and let's make it bigger. And I think it's a piece of cake to construct it. Thank you so much for watching.